Let's consider an atom. An atom is a quantum system made up of a heavy nucleus with positive charge and some electrons orbiting around it. The different ways an electron can orbit around the nucleus are quantized. They cannot do anything they want, the way they want, and with the value of energy they want. They are restricted to specific orbitals. Once we know in which orbit the electron sits, then we know the state of the electron. To simplify the explanation that will come after, let's consider a simpler model of our atom, restricting to the number of states that the electron can take to just 2. One with less energy and closer to the nucleus, which we will call the ground state of the electron, as we cannot go any lower, and a higher energy state receiving the name of excited state. A priori, there's no mechanism that allows the electron to move from one state to the other. These states, for an isolated atom alone in the dark, are referred to as being stationary, so an electron in one state or the other will remain there forever. But we know that physical systems tend to have the minimum energy, as a ball rolling down a ladder, and the same thing will happen to this electron. Its excited state is not stable, and there's some probability of observing the decay of the electron down to the ground state spontaneously by a quantum jump. In the process, a photon, a quantum of light, is emitted in a random direction, and it will have the same energy as that between the two levels of the electron. This phenomenon is called spontaneous emission, and the way to describe it in quantum theory is by taking into account that the atom is not really isolated. Actually, it is embedded within a quantum field, the electromagnetic field, which can fluctuate randomly at any point in space. This will be the mechanism that allows the transition of the electron. Initially, there's just an excited electron with no photons present, or in other words, the field is in its vacuum state. But as the field fluctuates, there is still an interaction between them known as the electric dipole interaction. This fluctuation gives the path to irreversibly give the energy of the electron to the field as a photon, enabling the electron to reach the ground state. The probability of observing an emission event over time is characterized by the decay rate gamma. If gamma is large, then the time we need to wait to observe a jump is short, and vice versa. This corresponds to the population in the excited state decaying exponentially with this rate. This phenomenon can be understood as a particular case of the behavior of an open quantum system. That means a system that can interact with its environment. The environment, or also called the bath, is nothing else but a larger quantum system that is not bothered much by the smaller system, as dropping an ice cube in the sea will have no effect on the sea's temperature but a huge impact on the pure piece of ice. There are many ways to deal with open quantum systems in quantum mechanics, but the one that we will use today is the quantum master equation formalism. This formalism wants to describe the evolution of a system forgetting about the environment, hiding all its contribution under the carpet as constants or operators. The evolution of the system over time is described by two contributions. The first one is the coherent evolution, the one obtained from the Schrödinger equation and would be the only contribution for the case of a closed system, and the second one, the dissipator, is where the incoherent part of the evolution comes in, taking into account that energy that seems to be leaking out of the system. We can see the jump operators moving the population from one state to the other, weighted by the decay rate gamma. Let's imagine now that instead of a single atom emitting spontaneously, we have many identical copies. We may think, from what's been said before, that each atom in the ensemble will do its own thing and emit daylight in any random direction. As a consequence, the emitted light would be that of a single atom multiplied by n, the number of atoms. This is exactly what we would find in a dilute quantum gas, no problem yet. Nevertheless, we need to think again about the interaction that allows these emissions. The interaction between a specific atom and the field not only modifies the state of the atom, but does so with the field. This can lead to making it interact with a second atom, what would effectively be an interaction between the two atoms. Now there's an interaction between atoms mediated by the field. Because of this, the decay and radiation emission of one atom is related and coupled to all the other atoms, given by the gamma sub A and J, where A and J are labels indicating the pair of atoms it corresponds to. This coupling depends on the distances between these and the directions of the atoms. When atoms are well separated, as it happens in a dilute quantum gas, the coupling between atoms becomes negligible and behave independently, with no correlation in the photon emission. However, in the opposite limit of having the atoms really close together, much closer than the wavelength of the emitted light, the interaction becomes stronger. In this sub-wavelength regime, also known as the Dicke limit, the emission of a photon cannot be attributed to any specific atom but to the ensemble as a whole. The behavior of the atoms is no more independent but collective in this sense. Consider our atoms with a full inverted population. Instead of being in the ground state, all atoms are in their excited state. A quantum fluctuation of the field makes the first spontaneous emission happen, and as the atom responsible for this is unknown, the state of the ensemble can be described as a superposition of all possible states with all atoms excited except of one of them. As the atoms are really close together and their couplings are really strong, the emission of a second photon is enhanced, and the state of the ensemble after that will become again a superposition of all states with two atoms in the current state. The enhancement can be seen from the decay rates, that are not equal to gamma anymore, but they are now n times larger. At each emission, this decay becomes larger and larger up to a maximum proportional to the number of atoms squared, so each emission takes place in a shorter time. The successive photon emissions happen one after the other very rapidly and highly anisotropic with a preferred directionality, giving rise to an emission burst being completely different from the independent case discussed before. This phenomenon is called superradiance, the enhancement of a spontaneous emission in an ensemble of atoms due to the dipole-dipole interactions of its constituents. All the states of the ensemble we've gone through during the superradiant burst are known as radiant or superradiant states, and as it has been said, they correspond to superposition of states with the same excitation number. These superpositions are symmetric, meaning that the exchange or permutation of any two atoms leaves the state the same. But there's a bunch of states that the ensemble can take that don't respect this symmetry. These states are, some of them, known as subradiant, as they don't show an enhanced emission but a suppression of it. Their decay rate is close to zero, so to observe a single emission event, we will need to wait a really long time. These long-lived states couple really badly with an external field, so they are difficult to excite. Not superradiant states, which come up naturally with the evolution as it has been described. The different behavior in light emission of superradiant and subradiant states can be understood from a classical point of view. A classical oscillating dipole is the tiniest antenna anybody can imagine, as the movement on charges generates an electromagnetic wave propagating through space. Now, having a set of these oscillating dipoles, each of them generating waves, these will interfere at each point in the space. If the dipole oscillate in phase in a given direction and are really close together, the interference will be constructive and the radiated energy will resemble that of a largest dipole, as it happens in superradiance. On the other hand, having dipoles out of phase will give rise to a destructive interference suppressing any emission of radiation, as we have seen for the subradiant states. Everything we've been talking about up to now applies to any configuration of atoms in space, like a bunch of them in a really small volume fulfilling the Dicke limit. But the interference effects are more prominent if there is a certain structure or order in the way atoms are located in space, so they can be harnessed as we like. For instance, let's think of a long linear chain of atoms, like an infinite chain. In this case, because of the discrete translational symmetry, the states of this ensemble correspond to the Bloch states, well known from condensed matter physics. These states have a well-defined quasi-momentum, and there's a clear connection between the collective emission we've been talking about and this property. When a state has a quasi-momentum larger than the wave number of light, then the mode is guided, meaning that the light is confined within the chain, only being able to escape from the ends. These guided modes are, you guess right, supraradiant states. Lots of other phenomena and effects come from the enhancement or suppression of emission in an atomic ensemble, and from these ideas physicists have found ways to apply them in quantum technologies. Those that I will talk about today are mostly related to subradiance, as having a long-lived state can be useful for a lot of application. The emission burst from superradiance leads immediately to the idea of a laser. Both are sources of coherent light but have some differences, mainly that the laser uses a stimulated emission of a gain material within a really good cavity, a cavity that must be protected from external perturbations, as simply thermal vibrations, in order to maintain the frequency constant, their color constant. On the other hand, superradiant lasers operate in the bad cavity regime, where photons are not responsible for the coherence of the emitted light, but it's the atomic ensemble instead. These lasers can operate without bothering so much about the cavity fluctuations, being a reliable tool for precise measurement of frequencies, time, and distances. Subradiant states can be used for a single photon storage, but we've said that it couples badly with the light, so no subradiant mode will be excited when an external field is applied. There are several ideas to address these states for this purpose. One of these is using a tunable linear combination of superradiant and subradiant states called gray states, as they are not absolutely bright and not absolutely dark. The tunability of this combination can be performed with an energy shift of the energy levels in the electron of one of the atoms, controlled by an external field. We can make a change in real time from a radiant state able to couple with light to a subradiant one, so the photon won't be able to escape. An alternative way to address subradiant states is the interface of an atomic chain, where atoms are really closely spaced, with the evanescent field of a nanofiber. In this case, a guided mode of the nanofiber with the right frequency will efficiently couple to the guided modes of the atomic chain. It leads to the existence of modes with an enhanced spontaneous emission into the fiber, while the radiation into other free space modes are suppressed. These states are often referred to selectively radiant states. By changing the geometry of the array from a 1D structure to a square lattice in 2D, there's no need for any nanostructure considered previously. It has been seen experimentally with rubidium atoms in an optical lattice how, shining an external field perpendicular to the plane of the sample, there was an enhancement of the reflectivity, the amount of light that comes back in the same direction of the incident field. A subradiant state of the atomic 2D array was responsible for this, because of their highly directional and enhanced light scattering. In a sense, this is the smallest and thinner mirror ever conceived, and can be used as a single photon storage device, or a photon-photon gate when the array is made out of Rydberg atoms, which is a topic for another day. The last application I will talk about today is the improvement of atomic clocks. Atomic clocks are devices used to measure with high accuracy the frequency of an atomic transition, in order to use it as a way to measure time. The standard protocol to measure the detuning between a laser and atoms in a sample is by the Ramsey protocol. It consists of 3 steps that can be visualized in the Bloch sphere. Starting with all atoms in the ground state, first we apply a pi-halves pulse that brings the state of the atoms to the equator of the Bloch sphere. Then a free time evolution dependent on the detuning takes place, leading to a precession around the equator. Finally, a minus pi-halves pulse is applied in order to measure how much population goes back to the ground state. The population imbalance depends on the detuning, and the precision of this measurement depends on the time of precession, on the order of the inverse of gamma. Thus, if we were able to have a larger time span to measure the accuracy of the transition, the frequency measurement of the atom would improve. So accessing a subradiant state during the evolution with their near to zero decay will improve the protocol outcome. The interest in collective phenomena arising in atomic ensembles interacting with light is increasing over time, as the conditions to test the theoretical models proposed decades ago into the lab have been achieved. Cold quantum gases in optical lattices and tweezers, the usage of superconducting qubits and quantum dots, and the leverage of waveguides to enhance the long-range dipole-dipole interactions between emitters allows to explore all the richness of these states, how they unveil new clues for the behavior and properties of many-body quantum open systems, as the study of dynamical phase transitions, correlations and entanglement between different parties. They can help to develop new approaches to quantum technologies.